Okay, so we've looked at the structure of atoms, we've looked at the law of conservation of mass, we've seen how these things go together. Now we're going to start looking at a couple of new techniques that give you a bit of an insight into how these things have been determined experimentally. So we're going to be looking at relative atomic mass and mass spectrometry, which means we're going just a little bit beyond the idea of a mass number and actually determining the relative mass of each of the atoms. So you probably haven't thought about it, but when we buy really large amounts of things, if we're buying large amounts of nuts or bolts or nails at somewhere like Bunnings, or even in the case of if you've ever emptied out your money box and you've taken it to the bank, you'll find that a lot of times they will weigh bags of coins. And essentially by weighing, what they're doing is counting how many individual items there are. They do this when there's so many of them and the mass of the individual ones can be known, so they just end up working out relatively how many there would be based on the mass. For chemists, atoms are way too small to be able to weigh individually. We can't possibly weigh out a single atom. So what we need to be able to do to work effectively is bring the atomic scale into the macroscale world. If we're weighing out a gram of a substance, we need to be able to know roughly how many atoms or molecules are in that substance, so that we know when doing reactions that we can put them together in the right proportion, remembering that our chemical equations give us definite proportions and our formulas give us definite proportions. So we kind of need to get those right in order to be able to have them to react in the right way. So we do this by setting a couple of standards and then measuring things relative to each other. We've seen this already when we look at protons and neutrons. We said that they have a relative mass of 1 AMU and a relative mass of 1/1860th AMU for electrons. We looked at the actual size of these, which is far less than 1 gram in the 10 to the negative 26 kind of scale. So we know that they're not really one anything, they're just one relative to each other. Okay, so 1 proton is going to equal 1 AMU, so 1 atomic mass unit. 2 protons would be 2 atomic mass units, or 1 proton and 1 neutron is going to be 2 atomic mass units. We also know that we have isotopes, that we can have 1 proton, which makes this hydrogen, and then in the case of 1 proton and 1 neutron, this is going to be deuterium, which is still hydrogen, but it's heavy. You may have heard reference to heavy water. Heavy water contains deuterium as its hydrogen atoms rather than just hydrogen. And then tritium, which is a 1 proton, 2 neutron hydrogen atom. And you may have asked how we actually know these exist. Well, we know because the number of protons and neutrons contribute to the overall mass of the atom, and then how many of these isotopes are around contribute to the average atomic mass that we see. Okay, so in the 18th and 19th centuries, is a great time for science, and there were a number of experiments that were conducted to determine the mass of different elements relative to one another. Okay, so this isn't their actual mass, just relative to one another. It's not an exact measurement because it's not possible to weigh a single atom, but it does give us an idea of how they increase steadily as we continue to add protons. These days we have a mass spectrometer, which will actually give us the specific mass, relative mass to charge ratio of species that are put into it. So we can actually see those different isotopes now quite clearly using a mass spectrometer. So all atoms exist as a combination of a few of their isotopes. Okay, so the relative atomic mass is defined as the weighted mean average of its naturally occurring isotopes. That being that it's just like averaging them out, but we also need to take into consideration how much of each there is. So if something is 90% of one mass, clearly it will be closer towards that mass than the 10% of maybe the lighter isotope that it may have. So we need to take those percentages into account to be able to accurately work out their mass. So we define this as RAM, or relative atomic mass, and it is actually defined against carbon. Okay, so this has been defined as one atomic mass unit is equal to the same mass of 12 grams, 12 units of carbon-12. So we know that carbon-12 has 6 protons and 6 neutrons, which means by saying that this equals 12, then anything with 1 proton should equal 1. And this is exactly how we get the mass of hydrogen. It's not actually 1 because it was defined as 1. Carbon was defined as 12, and because hydrogen actually happens to be 1/12 of carbon-12, we see it as being 1. And you'll notice it is actually just a little over 1. This decimal place here is because of really small amounts of hydrogen-2 deuterium and hydrogen-3 tritium. Okay, so the relative isotopic masses, okay, so this is the mass of each isotope, are used rather than true masses for individual atoms because true masses are very small. So remembering we're keeping it relative because dealing with large exponents is a bit annoying. So pretty much the majority of elements exist as a number of different isotopes. Okay, fluorine is unusual. It's just all one isotope. We only ever see fluorine 19. Lithium, we can see lithium 6 and 7. Chlorine, we've already been introduced to as 35 and 37. We can see here that krypton and tin actually have a number of isotopes. Tin has quite a few isotopes. And these relative abundances are actually set at the time that the elements were created in the universe. They don't change. So we use a mass spectrometer, which is just a machine that has a computer attached to it to confirm the existence of isotopes and determine their relative abundance. We can place a sample of a substance into the mass spectrometer and it will spit out a graph and some data that tells us A, the relative atomic mass of the atoms that we've placed in there, and B, their abundance with reference to each other. Okay, so the underlying principle of this is that the movement of charged particles will change as they pass through a magnetic field, and we'll look at a schematic of what the machine looks like. The particles are deflected from their original path, and the degree to which they deflect is reliant on their mass and charge. This is sort of like a bowling ball, if you think about a bowling ball and a ping pong ball analogy. If I roll these across the table, the bowling ball's momentum, it's got a lot more mass, it will travel a lot faster, and it's going to be harder to deflect, whereas a ping pong ball, it's going to have a lot less mass. So if we were to blow on it or pass it through a stream of air, it would turn a lot more readily than what the bowling ball would. Okay, and the same thing says for atoms. What we want is small, highly charged atoms will be deflected more. Okay, they're affected by the field a lot more. We don't need to know the specific sequences of this anymore, so don't worry about learning all the parts of the machine. This is essentially what happens. We put in our sample. It's actually submitted to, through an electron field which knocks electrons out of it. So we have our molecule or our sample, our atom, we shoot electrons at it. Those electrons have the capacity, if they hit, can knock an electron off the atom, which will mean it becomes positively charged. So we shoot electrons at it, we get a positively charged atom, and then 2 electrons being spat out. Okay, so they come in, they're charged, they pass through a magnetic field, that magnetic field, because they're charged, the magnetic field, the electric field accelerates them. So this is an electric field here, okay, not a magnetic field, and the electric field accelerates them, causing them to move faster, and then they come down this tube. This here is a magnetic field, and as we said before, the level of deflection that they experience is dependent on their size to charge ratio, and then this detector here detects how long and the number of particles that go through. So if we put through a sample of neon, we would see 3, neon 20, neon 21, and neon 22. The height of these peaks relates to the relative abundance of the isotopes. Okay, so if we were to look at this one here, we can see that the element that was placed through here had a relative atomic mass of 208. But there was also isotopes at 207, 206, and 204, and 208 would be the most common or the most abundant of the isotopes. So, as I said, you don't need to know the details of the machine. It is good to have a bit of an overview of what happens in that our sample is turned into a gaseous state, so it's vaporized. Then it's ionized, so the electrons are shot at it in order to form an ion. Because we only detect, the machine only detects positive ions. Okay, so we have to knock an electron off it so that the detector will actually detect it. It's an ion detector. So if it's not charged, in fact, if it's not positively charged, the machine is not going to detect it. It just doesn't show up. The ions are accelerated through an electric field and then deflected by the magnetic field. Okay, and then that detection occurs and the intensities are measured. Okay, and then the intensity gives us the relative abundance. From that, the data is then recorded as what we refer to as a mass spectrum. With the mass spectrum, it's important to pay attention to the axes. Okay, so the y-axis is our percentage abundance, so the relative abundance of each ion. And then the other one you'll actually notice is the mass to charge ratio. So you can imagine if we were to knock 2 electrons off the atom, this charge would be 2. So if I had a relative atomic mass of 24 and I knocked 2 electrons off, the peak I would actually see is 12. We don't see that happening a lot. Most of the time we only knock off 1, which means if I was looking at something like magnesium, which has a relative atomic mass of 24, it would be 24 divided by the +1 charge that it has. So this gives us the actual mass of the cation that went through the machine. Okay, we'll look at this a little bit more and look at some examples where we see 2 being knocked off, but it's not a common occurrence on the things that you will see within the scope of the course. So if we look at this, this is an example of what the mass spectrum looks like. So this is of chlorine, which we have talked about having 2 isotopes, and we can see that we have the relative abundance here on the y-axis and the relative isotopic mass, which is our mass to charge ratio. Okay, and we have a large peak here, which the top of the peak corresponds to 75%, and a peak here, which corresponds to 25% here. The data is tabulated over here, and we can see that, yes, 75.8%, so if we had a ruler, we could measure this accurately, has a relative atomic mass of 34.969, and 24.2% has a relative atomic mass of 36.96. And when we see this on the periodic table, you should have noticed that the relative atomic mass of chlorine is actually given as 35.5%. Okay, it's a little bit above 35. Okay, it's closer to 35 than 36 because the majority of chlorine atoms that we find are 35, but it's a little bit over due to this 25% being a mass of almost 37, so it drives it above 35. we can actually work out the exact value of this using our relative atomic mass formula. So this is the first formula that you need to learn. This one isn't given in your data booklet, so you do actually need to learn. And this gives us the relative atomic mass of a symbol AR of an element based on the relative isotopic mass of each isotope multiplied by its relative abundance. So in this case, we would add, for chlorine, we would add the other relative isotopic mass multiplied by its percentage abundance onto the top line there as well, and then divided by the total relative abundance, which of course, because it's a percentage, is going to be 100. This formula you need to know. You need to know the definition of relative atomic mass in terms of its relative nature compared to carbon-12 equaling 12 units. In the next video, I'm going to do some sample calculations and show you how this formula can be used.